All right, let's start again. Oh, I'll just put this over here, so it's not in anyone's way. If I'm going too fast, just come out here and turn the sign round. Okay, let's go. Now I want to look at an ADT, and we're going to look at it in C, and then we're going to look at it in Java. So we'll look at the stack ADT, and we'll look at the very one we used last year. Now, just lights. Is that bright enough up the back? It's okay? Here we go. Contract, invariance. Okay, so you know the idea of an ADT is that there's a contract. We're going to have millions of entities in our system now, and we're not going to have someone in charge telling everyone what to do. Everyone's going to be free agents. So in the market, how does it work when everyone's free agents? What stops everyone stuffing everyone around and not doing stuff and things like that? There are these things called contracts. You have all these free agents acting to optimize things for themselves, but they enter into binding agreements. And these agreements are, I guess, replacing the Pharaoh. So the binding agreement is, in the computing, at least of the form, you give me, you call this function when these particular things are true, and I guarantee I'll do this. And that's called your contract. So programming by contract is where you get the different parts of the system to agree to contracts. And the important words, and you probably remember all these, are invariants, postconditions, and preconditions. Invariants are the things that are true before and after any interface function is called. Preconditions are things that have to be true before the interface function is called, and a postcondition is what's true after it's called. So I'm saying to you, if you call this function, you call that function, and the invariant is true and the precondition is true, then after that function is finished, she promises that the invariant will still be true, and now the postcondition will be true. That's the binding agreement you enter into. So for example, for a course, I promise that if you come into this course having understood everything in 1927 and having understood everything in 1917, that's a precondition, and the invariant is, and, what's the invariant? And you are still alive, then I guarantee that at the end of the, no, I can't make that guarantee.
Also, understanding 1917 and 1927 are invariants because they should still understand it by the end of 2911.
Yeah, it's an invariant. That's no, I'm not guaranteeing they'll still understand it at the end. I can't guarantee that. That's not my job to make sure of that. I mean, they'll probably try and make sure of that. That's right. So it's just a precondition then. The precondition is if you understand 1917 and 1927 at the start of this course, the contract we're entering into is that at the end of this course, I guarantee you will understand 2911. Now, maybe I won't live up to that contract, and maybe there are bits you're missing, but that's essentially our relationship. It's a contract between us. This is programming by contract. Once we have the contract, we normally write tests. You know our way of writing stuff. We have the contract, we work out, we think of a new ADT, we're coming up with a stack ADT. What's the contract for a stack ADT? You call new stack, I'll give you a stack that's empty. You call push on a stack and give me an element, I'll give you back a stack which has that element at the top, and the rest of the stack as it was before. The contract for pop is you call pop on a stack, the precondition is stack's not empty. I guarantee that I will give you back the top element and have, I think our pop also adjusted the size of stack at the same time. I don't know why we did it that way, we just did. All right, there are pre and post conditions. Once you've worked out your pre and post conditions, once you've worked out the contract, the next thing you do is write some tests to enforce the contract. Then you run the tests and everything fails, of course, because you haven't written the program yet, and then you write the program and you run it and you check it passes the test, and that's our approach to everything. And those tests are called unit tests because they're testing the small units of your program, the tiny individual parts of each contract. And your program could end up with thousands and thousands and thousands of little internal contracts in it, and your unit test should check all of those. So let's look at our stack.h from last semester. Here we go. I've got a pointer stick. Yes, we do. So type, oh, hang on. This isn't such a good pointer. So we've got our abstract type stack, and it's a pointer to a struct. We've got a couple of interface functions, something that creates a new stack. That doesn't take any input in, it just returns an empty stack that's new. something that pops a character off a stack. So this must be a stack of characters. So given a stack, if that stack's not empty, it will return a character that's at the top of the stack and also update the stack. It's got a push function that given a stack and an element, pushes that element onto the top of the stack. And it's got a function called isEmpty, which given a stack returns true or false, which in C we encode in an int, telling you whether that stack is empty or not. It's in a .h file. I don't know if you can see that. How are you going at the back with that font? Is that easy to read? I'll make it one smaller and tell me if it's still easier. Still okay. Can you read that? At the back? I want to see no's, really. Are there any no's? Is there no? Someone said yes, meaning no? It was poorly specified on my part, wasn't it? Wave at me if it's a bit small now. It's a bit small now. Can you sit closer to the front? Yes? Thank you. I think if you can't see it, sit closer to the front, only because the very next slide has so much on it that I want to put it all on the screen at the same time. If you can't see from the back, then I reckon next lecture come in and sit a little bit closer to the front, because this will probably be the size font we use when we look at code. And it is a bit small. I've tried it out myself a few times. I can see it with my glasses on, but it's hopeless with my glasses off. Mind you, I can't see any bugs in it with my glasses off, so I often code that way. Okay, so the people that can't see, do you want to just move down, or wait a minute while you just move down a little bit, just so you can see it? Was it you? Did you want to move? No. All right, so that's the .h file. So now we know our the functions that are in the interface, and I sort of verbally gave you the contracts. Notice that just knowing the names of the function doesn't really tell you the contract. The contract is what we call a semantic contract. Like it has meaning. Semantics is meanings. So just knowing the names of the function, that's syntactic. So I guarantee there'll be functions with these particular type definitions. But the contract's more than that. And all these other properties hold and so on and so on. And normally they're just implied or inferred, or I write it in comments. But often you can have something that satisfies the syntactic contract fine, but actually doesn't behave like it should behave. And this is one of the banes in computing, is making sure you specify the semantic contract properly. And of course we never do, and we change it all the time anyway, as we spoke about yesterday. So it's actually really important when someone has written something to a contract that you test that they have complied with that contract, because they might have a different understanding of the contract, completely valid interpretation of the contract that's different to yours. When I buy a car, I just want to talk about two different sorts of testing. When I buy a car and I'm driving it out of the showroom, this happens to my brother-in-law. I'll tell you a very sad story that happened to my brother-in-law. He bought a new car, Peugeot. He was telling me how absolutely amazing it was, and it just sounded fantastic. And they drove up to Brisbane in it just before Christmas on a really hot day. And just outside of Gosford, the car exploded. And they had to get out of the car. And then they were really depressed, and it was hot, and no one would come for hours and hours to pick them up, and the whole family was sitting in the car, and they'd got up at 5 o'clock in the morning to travel to the Gold Coast. So they were just all depressed, and they're sitting there by the side of the road, and then one of the guys, what's that? And it was leeches. And they'd sat on a whole lot of leeches, and a whole lot of leeches were crawling. So they're flicking leeches off them, and it's just disgusting. So they're not in a good mood. And they ring up Peugeot, and Peugeot say, yeah, look, you can return the car and we'll give you a rental car, but you'll have to return it to Sydney Airport. So they had to then work out how to get a tow truck to take it down to Sydney Airport, and then they had to catch a train all the way down to Sydney Airport, and then they got a rental car and drove on. And they were really depressed and cross. So they went up and they came back, and the car got fixed up, and they went and picked it up. And they got it all sorted just before he had to fly over to England to do something, and he wanted to make sure the whole family had the car while he was away. And they got the car back just in time. And then driving to the airport that morning for him to catch his international flight, then the car exploded again. Now at this point, what are they thinking? Assassination. They're thinking, I do not want this car. I do not want this Peugeot. They've tried to fix it twice and they haven't. Either Peugeot sucks, or quality control on this batch sucks, or I'm just unlucky. But there's something bad with this car. I don't want to give it to them and them take it away and say it's fixed again, because I have no confidence now. They're just going to be crap. When you're the client, there's a whole lot of things happening on the hood and you can't see them all. When you're the manufacturer, when you're the person writing the code, you check everything. So you're putting the engine together, you run a million billion tests on it, unit tests. You write somebody to check that the pressure on this valve is right, and you write a unit test to check that the fluid through this pipe's correct, and the torque on this thing is correct, and the stress on that's correct, and the pressure doesn't change too much, and this has a certain amount of this and that. You just check a million little tests on it, and they're all called the unit tests. They test all the little things. But when the client comes along, the client can't test all those things and doesn't really care about it. What does the client want to happen? He just wants it to work from their point of view. At a really high level, they want it to work. Testing that it works from the client's point of view would be what? You'd get it, you drive around the block, it's got to feel good. If you're writing a review for a magazine, you're reviewing a car for a magazine, what do you look at? You look at how quickly it accelerates, how comfortable it feels, if it's nice and spacious inside, if the indicator's in the right spot. I don't know what they do. They drive around and write their feelings down. Whatever they're writing down, whatever testing they're doing, that's called acceptance testing. That's what you do to convince the client that it's a good thing. Can you see that's different to the unit testing? The client doesn't really care that you tested the fuel flow through this pipe at that speed, with that velocity, at this temperature. They just care that the overall system behaves. So in this course, we're going to expect you to write unit tests, just like you've been doing all the way along. On everything you do, you're going to write little unit tests just to check it's correct. And then when you give the code to your boss is going to run acceptance testing on it. And that's going to check, it sort of does what the boss expects it to do. Now you would think if all the unit tests work, then the acceptance tests are going to work. Yeah, you think that. But you understand there's two different sorts of tests. So we're now just going to do some unit testing. So what's the unit testing for the stack? Well, let's think about it. This is the actual code we wrote that year, back on the 18th of the 8th last year. You may well remember this code very fondly. What did? We hash included stdlib, stdio, assert, and stack. We gave prototypes of some functions. We gave our main function, which does all the tests. It called 3 void testing functions. And then at the end, it printed all tests passed. What should it have printed?
One test passed.
No. What do we always print at the end of all our unit testing? You are awesome. It should have said you are awesome. I'm sorry it didn't say that. Okay, and then it runs these tests, and here are the definitions. This is all static, of course. This is what happens at compile time. Here's the function, test new stack, prints out I'm about to test a stack, creates a stack using the new stack function, because we noticed every ADT has to have a function to create an element of the ADT, because the type is hidden from everyone. Only the ADT itself can create an element of the ADT. No outside person can, because they're not allowed to know its structure. So there's always a new style function in your interface. So we're making a new stack. We're asserting that it's empty. So now we're checking the part of the contract that when you call the new stack function, you get an empty stack. So that's our first test, our first unit test. Woohoo! We should destroy the stack now, because remember, the stack's going to be created using malloc. It's C. If we don't do a free now, we've just done a memory leak. Because it was a short test program, we didn't put it in, but we're feeling guilty. We're thinking, ooh, I should have put a destroy stack function in my interface. Now, whenever anyone uses a stack, there's a memory leak. There's lots of things wrong with this stack implementation. So that's just one of them. Now we look at this next function, test is empty. How does that work? We create a new stack. We push some things onto the stack, and we check that it's not empty. And if it's not empty, we go, woohoo, it passed. You can see we're not testing every possible case here. We're just testing a couple of things. And then we test that a push works. How do we do that? And we're testing pop as well. We make a new stack. Don't forget to delete this at the end. We did. Check it's empty. We just made it. Push something onto it. Check it's not empty. It isn't. Pop something off it. Check it is empty. Woohoo! That's checking that push and pop work. But it's not quite checking, isn't it? Oh, and we're checking that the value it pops off is the value we pushed on. So we wrote these tests before we wrote the stack. And now let's actually implement the stack. I like implementing code like this. It's as easy as just clicking on a button. Stack.c. Here's stack.c, our implementation of the stack. We include all these libraries. We have to include them because certain functions we use, the linker needs to know where to find them. They're in these libraries, stdlib.h. They're in the stdlib library, so the stdlib.h gives us their prototypes. What do we get from stdlib.h? Do you remember from C? What do we want from there? We get exit success, we get malloc. Yeah. What do we get from stdio? Printf, yep. What do we get from assert? Assert, okay. We're including the interface. Remember we put our interface in the .h file that we saw first? That's a description of the interface, the prototypes of all those functions. Remember C has this funny thing, you need to give prototypes of the functions before you give the functions, because C likes compiling in one pass through the file, and if it ever sees the name of a function that you haven't previously defined, it freaks out. So you declare all the functions up the top, and then you can order your functions inside in any order you want, and the program won't freak out. Otherwise, you'd have to sort of order them in reverse order, which would look weird. Wouldn't make sense in a sort of bottom-up way. Okay, so here's our ADT. This is an ADT, and it's a type def. Here's the actual type structure of our stack. Our stack contains two things. It looks like it contains an array of chars, and it contains int, which is a count of the size. Because remember, In C, there's no way, oh no, this isn't that. This is how many things are actually on the stack. And the stack is of size max stack size. So this is another flaw in the implementation. I didn't see anything in the contract about you can only push 100 things on, and then you'll get an error. But we're only creating an array 100 big. But luckily C has an extra feature that you can actually push beyond the end of an array, and it doesn't always cause a crash. So maybe we'll be able to get to 101 or 2 before we crash. So, and then we've got our function that creates a new stack. How does it do it? It mallocates, mallocation. It does a mallocation exercise, and it works out how big a stack should be in bytes, and then it requests that many bytes. It's automatically cast to the right type to be a stack. We check it's not null. That means we check that the malloc worked. We haven't run out of memory. We assign it its initial value. We just say, oh, the stack is empty at the moment, and then we return that new stack. Is that cool? And what else have we got here? Popping off. It's easy enough. We just reduce the index and return the top element. Push, we've got asserts to check our pre and post conditions. So we check for the pop, for example, we check that the stack's not null before we do the pop. We're checking our contract, and we check our contracts with asserts. And with push, we're checking that the stack's not full. Though if it is, it's going to surprise everyone because the contract doesn't know about that yet. And we put the new element onto the next array position, and we increase the item count size. So we notice that we've increased the number of items on the stack. And is empty, we just check that the stack isn't a null stack, that it actually is a stack. And if it is a stack, then we count how many items are on it with that field. We return that field, and if that's 0, then we say it's empty. So it's very, very simple, and it should all look familiar, and we all wrote this code last time. And that's what it looks like in C. And now, what I want to do is rewrite this in Java. So that's an ADT in C. It's getting close to an object, because we're trying to enforce this encapsulation thing, and we're trying to give it an interface, and we're going to do all that in Java. So it's looking a bit like a Java object. Let's actually write it as a Java object. How are we going to do it? Let's do it on this laptop down here. Here's one I prepared earlier. Ding. Okay, so let's get the source code from the internet. Let me just think for a second. Which one do we want to write first? We actually want to write our test first. I've put them in the wrong order here. Let's get our old stack, teststack.c, and let's make a Java file by copying the old C program, because the syntax is so similar, and we're just going to make a few little changes to it. So there's our old code. Let's just get an editor open. That's the editor we used yesterday. Let's make a new file. File, new, with the clipboard. All right, so that's our C program. And let's call it teststack.java. Teststack.java. Because Java files all in with .java. And this window is too small. What if I make it like, no? Okay, here we go. So here's our file. Let's change it. Well, the comments characters are still the same, but it's not teststack.c anymore. It's called teststack.java. Remember, all our class files start with a capital letter because it's going to be a class. Even the testing code is going to be a class, it turns out. So it's capital letter, created by Richard Buckland on that date. That's wrong. What's the date today? 4th of March 2010. Copyright. Oh, yes, definitely. It's very copyright. And there we go. Okay. Now, all this hash including, that's there, so C knows where to find stuff. But Java has a simpler way of finding stuff in some ways, which is you tell it where stuff is, and it finds it when it needs it. So you don't have to upfront say, I might be finding it here, I might be getting stuff out of here. It won't look till you ask, so we can just kill all of that. And now we've got the prototypes of all our functions. Well, Java's a two-pass compiler or a multi-pass compiler, and it doesn't require that it's seen all the names of functions before you use them, so it doesn't need you to declare them up front. So it makes our program a bit simpler. Now, everything in Java is a class. So, and if we want the outside world to use it, we have to call it a public class. So we're going to say public class test stack, because remember we're writing our test code now. And we better put a brace at the end. Is this font too big? No, sorry, I'm asking the wrong question. Can everyone at the back read this font? If I made it smaller, I'm going to ask the same question again. I think I'll just do this. Yes. How about that? Can you still read it? Ah, fantastic. Thank you, guys. All right, so here's our test stack class. And I opened the class, so I'm going to have to close the curly brace there. It's another curly brace language. And I'm going to have to indent everything in the middle, which this editor, luckily, I think just does easily for me. Okay, so everything's inside test stack, and I've got to make sure that test stack is the name of the file, and test stack is the name of the file, so everything's looking good. Woohoo! Got all the sort of syntactical stuff out of the way. So our first function, our calling function to start the whole ball rolling, to start the simulation. Before we're going to set all these objects up, and we're going to ask the objects to do stuff, but there has to be someone to say start the simulation. And that sort of doesn't necessarily belong to any object, does it? It's just someone saying go. So that's the main function, and there's no objects created when the program starts, so the main function doesn't belong to any program, to any object. It's a static function. It's something that exists at compile time. It's not something that exists. It's not. Most things, if we go back to this world here, in Java, are going to exist at runtime. Most things are going to be dynamic. The objects are going to be created, and we're going to call the functions on things that have been created. It's all going to happen dynamically. But to start the thing off, because in a sense nothing's happened, we need a static thing to start it off. We need something that's still there at compile. I'm not explaining it very well. Wait till we get to definitions of static later on. It will become clear. At the moment, static. Static int main. Does main return an int? No. In C it returned an int because that indicated whether the program had worked or not. Java has more sophisticated ways of communicating with the outside world, and it just doesn't return a code to say whether it worked or not. It can return a million things and interact with the world in a million structured ways. So this way of just returning a value is a bit crude. It doesn't do that. It returns nothing. Remember, it takes as many arguments as you want, and it doesn't need to keep track of the number of arguments you passed in because we're going to store them in an array of strings, and in Java, arrays know how big they are. So we don't externally need to store that information. Arrays are essentially objects. So you want to know how big they are, you ask the object, how big are you? And the object looks after itself. It tells you how big it is. So we don't need to keep track of the number of things we've got. We just need the array. Now, this is an array of strings. And in C, a string is a char star. It's very confusing, isn't it? It's a pointer to a... In Java, a string is called a string. It's an object, so it starts with a capital letter. Now, this is C syntax. Let's look at this. This is a bit funny, isn't it? We always grumbled about it when it happened in C. This is saying, in the land of C, not in the land of Java, arg is an array whose elements are strings. C played that little game. Do you remember that game? You have some expression on this side that evaluates to a type, and you give the type on that side, and by playing that game, you can eventually work out the type of this. But can I just ask this in normal English? If arg is a type that's an array whose elements are strings, what type is arg? What's a simpler way of saying the type of arg? I could say, oh, arg is a type which is an array whose elements are strings, or I could say arg is an array of strings. I could say, in other words, array of strings, yep, that's what arg is. And this is how Java does it. It doesn't play that little C game. So that's looking good so far. Do we return exit success? No, because we don't return anything. We're a void function. Woohoo! Now, what's the chance that this is going to work as it is now? 0. Let's check that. Save. I've saved it. All right, let's open a little window. Because we like playing, don't we? We like trying things out, checking them out. Here we go. So we're going to go ls, am I in the right directory? Yes, test stack's there. So how do I compile it? What do I say? javac test stack dot java. Only 3 errors, that's not bad, given it's essentially a C program. I've scribbled out the word C in crayon. So what doesn't it like? Well, it doesn't like the void. Well, that's right. In C, when your function doesn't take any arguments at all, you have to say it's of type void because of a delightful compatibility feature C has, which is if you just give empty brackets to mean empty brackets, C thinks, oh, you meant to put an int in there, and sticks it in for you, hopefully. Java, if you give it empty brackets, it thinks you mean empty brackets. So that's really cool. We're not complying with the style guide, there should be a space. Okay, printf. Well, it's not called printf. What's it called? Println. And where is it located? System.out.println. And actually, you can probably, oh, that's not how you spell system. You might even be able to start to get a hint about what's going on, which will all become clear later on. This is a function. Remember I told you, except for static functions, functions all belong to objects. What object are we talking to at the moment when we're calling println, do you think? There's an object called system.out, and we're talking to system.out, and you're system.out, and I'm saying, hey, system.out, println, testing new stack. And he prints it out. See? I asked him to do it, he does it. Here's the object that knows all about the console, system.out. He knows all about the console. So in C, the default is it prints it to the console. You know, there's a more fancy version of printf where you can say where to print it to, the console or this file or that file. Well, in Java, every one of those things has an object associated with them, and you just talk to that object and say, print to your output device. So system.out, what's that?
To your output device.
Print to your output device. That's right. Oh, yeah. Stop saying that. Oh, okay. So now we're done. That's looking good. Did I see above we had a printf that we didn't replace? We've probably got some more. Oh. And need a wider window, don't we? Is everyone melting or is it just me? It's just me. You are melting? Someone suggested that everyone bring their own air. Everyone should be responsible for their own breathing. So if everyone could bring oxygen tanks tomorrow, that would be good. All right, so we've done all that. We've got some more voids we had to get rid of. And some more voids, because they take no arguments, so we just give them no arguments. And we're getting pretty close now to a correct program. Let me tell you what else has to change. We're going to have the same interface functions. Look at the first test here. We're testing a new stack. This is not how we create a new stack in Java. It's very close to it. Remember I said before we noticed that every single ADT needs to have a creating function, something to make a new one of them. If you're making a stack type, you need a new stack. You're making a queue, you need a new queue. You're making a graph, you need a new graph. You're making a chessboard, you need a new chessboard. Because, and that's only for abstract types. Because in C everything's abstract, all objects are going to be encapsulated properly, then every object's going to need to have something to make one of them. So it's actually going to be common across all objects. So Java said, well, we'll give it a common name then across all objects, because it needs to be there. So it's actually called new. So you just say, give me a new, and it will create a new thing of the type that you ask it to create a thing of. So here I'd say, stack, I want you to make, oh sorry, and one last thing to say before I get bogged down in details. Type definitions over here, static time, convert to, in C, type definitions here convert to areas of memory at runtime. In Java, the type definitions are called classes, the static stuff. That's what we're writing now. So classes here describe our types, and at runtime, when we make them, what do we call them? They didn't even really have a name in C. We just said, oh, areas of memory. But in Java, they're so important they've been given a name. What do we call instances of classes when we make the class at runtime? I might make 6 stacks. I've made 6 objects. Yeah. So at runtime, they're called objects. So the stack is like the recipe. I mean, the class is like the recipe. It's like the rules. It's like the static version of it. It's a definition of the type. And at runtime, when we make them, we're making objects. So objects are instances of classes. So we've got the class stack. This stack is going to be an object of that class, an instance of that class, and I want it to be a new one. I just say call, oh, it's not even a function. I just say I want a new stack. And in Java, the keyword new means make me a new thing of this type. So that's how you create an object in Java. How do you call a function on an object in Java? So I've got this object, this stack object here, with a little s, which is of the stack class, which has a capital S over here. It has some functions. Each stack object, I might make two of them, it's going to have the same functions. It's got the new function, it's got the pop, it's got the push, it's got the isEmpty. And this one also has a pop and a push and an isEmpty. How do I know I want to use this function or this function? How do I know which one I want to use? How can I tell the program which one I want to use? You say the name of the object, then you say dot, and then you say which of its functions you want to use. So we've just made an object called stack. Maybe I should have called it s, just so you don't mix it up with the name of the class. Yeah. So if I want to call the isObject function, isEmpty function on stack, what do I have to say? S.isEmpty. Notice the two differences. In C, we do it like this. We'd say isEmpty s. That's how you do it in C. And you probably notice whenever you made an ADT in C, except for the constructor, except for the function that made them, you always pass the ADT in as one of your arguments. And we sort of had the convention, we pass the ADT in as the first argument. Well, in Java, you don't pass it in as an argument because you're talking to it. It knows who it is. So you just put its name in the front so it knows who you're talking to. So in Java, you always say s.isEmpty. Hey, s, please do your isEmpty function, and I'll assert that it's not. I'll assert that it's true. Okay, so that's looking cool. What else do we have to do down here? This is all looking good. Okay, stack. We make a new stack. Looks like that. We're going to push something onto the stack. What would it look like? To push 4 onto a stack, what am I going to say? Stack.push. Pushes that character, which is the character 4, onto the stack. So you're sending a message to the stack, and you're saying, I want you to call your push function. I think they're the only changes we needed to make. There's one more function to make those changes. I've missed a push, have I? Oh, just below me. Yeah, thank you. Dun, 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 dun. So you can see this is slightly tedious. So I've actually stopped writing my programs as C programs first and then converting them to Java. Now I just write Java straight away. Done. All right, does that look right? Did anyone see any problems with that? Is there a closing brace? Yes, there is. It's all looking pretty good. Woohoo! File, save. Test stack, we're going to compile it. 9 errors. And hopefully, hopefully they're all the error we're expecting to get. What error are we expecting to see here? Oh no, here's one funny one. Oh yes, I forgot about static. I need to make them static. Yes, except for those 3 errors at the top, all the other ones I expected to get. All the other errors were saying, I don't know what a stack is. And yes, because I've forgotten to write stack.java. But I've written the test, because that was my object, to write the test first. But the other thing is, the static function main is not part of an object. It's static. Static things live on this side. They're compile time things. So main doesn't belong to an object. So when main calls a function, it can only call a static function, or it can call a function on another object it's already created. Functions on objects can call any of their own functions fine, but main doesn't belong to any object, so it can't call other functions. I mean, it doesn't have a family of functions that it lives with. It's not living inside an object. I'm saying it so confusingly. A static function can only call other static functions. Or it can call functions on objects. So if you were to, for example, over the weekend, want to do task 1, you would be writing static functions. You're probably not going to be creating many objects. You're probably going to be writing your Java code so it looks a lot like C code, and you're just going to be writing functions that are static. And only those of you who are adventurous will probably be creating objects. Most of you will be writing your Java code, writing some C code, and then writing Java code that looks exactly the same, and all the functions will be static because they won't belong to an object. But in the real land of Java programming, when we write into Java, rather than just replicating what we can do in C in Java, very few, if any, of our functions will be static. We have the one static main to start the ball off, and then from then on, every function we call belongs to an object, and we're just asking objects to interact with other objects. But I'm assuming this weekend you're just going to be sorting arrays and things like that. Okay, so let's save it and compile it. Did I make everything static? Is that all? Yep. Let's compile it, and hopefully I'm just going to get 6 error messages saying it doesn't know what a stack is. So we have to make a stack. Now, we could go through that whole process, and I did that this morning of converting stack.c into stack.java, but then I thought, oh, I'll just show you how I did it. So let's just jump straight to it. So let's go stack. Let's go back. Let's open stack.java in one window and stack.c in another window. And let's put those 2 windows. Wait, nope. Resize. Stop it. Don't do that. All right, here's stack.c. And here is stack.java. All right, so look at stack.c. Remember, we sort of looked at it before. It's pretty boring. It has a constant at the beginning, has a type def of the type, and then it just has the definitions of the functions. It's not boring, but it's fairly straightforward. You've seen that. Let's have a look at stack. Why am I getting a scroll bar? Ah, here we go. Stack.java. Okay, so let's just go down it and see how it's different. It's much shorter. And they're all available online, so you can check both versions out. Go through comparing them line by line. First of all, it's an ADT, so it's a class, in other words. That's our first cut at doing ADTs. It's a class called stack. So everything inside here is indented 1. So you lose, in object-oriented programming, you sort of lose 1 level. In Java, you lose 1 level of indent automatically because your outer thing's always the name of the class, and everything inside the file belongs to that one class, so everything is indented 1. It's sort of annoying. It's a pity you can't just unindent this 3 and then you could write everyone flush with the line. Have it poking that way, but you can't. I suggested to the Java standard when they were doing it that it shouldn't be called public class stack, it should be called lick class stack. Like with the pub missing. And then it sort of looks like, see, it saves you 3, see, you see it, yeah. Saving electrons, but no one went with that idea. Okay, here's, now in probably you can probably remember that we defined this constant, which was the maximum number of items that we're going to put on the stack, because in C, annoyingly, we have to declare, well, not anymore in C, but in the version of C we were using, you have to declare the size of your array at compile time. It's a static thing. At compile time, the compiler needs to know how big the array is going to be. So we had a constant, which was known at compile time, which we hash defined. And if you remember how hash defines work in C, they're like a macro moves over the source code before any compilation happens and replaces the input of the hash define with the output. So it's just a big global search and replace. Does a big search and replace before any compilation happens. Yes?
Two things. One, your item array should have the square brackets next to car.
Yes, it should.
And also, you should have a private static final int, because otherwise the constant will be replicated in every step.
Yes, it will. But static, I'm sort of sidestepping for a bit, okay. And Java will accept both of these.
Yeah.
Yep. Yep. So we're making, so in C, constants aren't actually done with something the language knows about. It's something that the preprocessor does. It just actually substitutes all the magic numbers in just before compiling. But in C, if we want a constant, we can actually have a variable that has a meaning in the program, and we just say final. In this context, why don't I do it? Like, oh, I can't, because it's a HTML page. But I should have moved those square brackets across. Now, why do we have the word private out the front there? Private the meaning of private in this context is the only people that are allowed to know about these fields, access these fields and modify these fields, or not people, the only functions that are allowed to know about, access or modify these fields are the functions that live inside this file, that live inside this class. So no one in the outside world is allowed to access these fields except the functions that are in this class. And if you can think about it, that's sort of exactly what we were doing with ADTs. Though in ADTs, to get that magic working, we had to, there's no way of telling C that other people weren't allowed to know about these type definitions. So we just arranged our hash includes so no one else got the type definition. When you hash included the .h file, you didn't get the type definition. So people hash including the .h file to get the interface functions, didn't get the type definition at the same time, so they couldn't use the type. But if they knew the type definition, they could have actually typed it in C into their files, and they could have accessed it. So we weren't completely stopping them accessing the functions, but that was our intent, and it was pretty close to it. Our intent was that only the interface functions were allowed to access the data inside the ADT. Well, in classes, that's exactly what they do, and that's actually enforced in the language, not through some syntactical hash include sort of fiddle that we do. If you say these are called the members of the class, so it's got these members here, or attributes, fields. It's got max stack size, the array, and the count are the three things that it has, and only, because of the word private, only the functions that we're about to list below are allowed to access these. No one else in the outside world, even if they did happen to know these type definitions, can access them. Perfect. Perfect encapsulation, perfect abstraction. So now we just list the functions in the interface. The first one's a constructor, the new function, and like I said in Java, the new's sort of taken for granted because they assume you're going to have a new function. So new stack, you actually just write as stack. So you just say the name of the type, and this is the function that gets called whenever anyone asks for a new one of them. So when someone says, give me a new stack, Java will go and look for a function inside the stack class called stack and execute whatever it does. And what the stack function does is exactly what the C stack function used to do. It sets the item count to be 0. Whose item count does it set to be 0? Its own item count. So which object is it talking about? Itself. So myself is called this. So like when I say, this morning when this got up, this spoke to this's daughter, and this's daughter wasn't able to work out the number of minutes in a day. Yeah, that's me, that's this talking about this. That's what objects do when they talk about this. They're talking about themselves, they call them this. So my item count is 0. My item, and remember item is an array of characters, is, and here's the equivalent of a malloc. Give me a new array of characters. Notice that the array, the size of the array that you want, is given in the code here. It's not given in the type definition. It's given at execution. It's given it until this instant when we actually make a new one. Java doesn't know how big that array is going to be. Unlike in C, where we know exactly how big it's going to be because of the type definition. So there's no reason you couldn't stick a different thing in here and make an array of a different size at runtime, or have two different options. And if the user selects this, make an array of this size, and if the user selects that, make an array of that size. So the arrays are decided dynamically, the array size. So this creates a new array. It initializes item count to 0. But boom, that's exactly what the old new stack used to do in the C version. Let's have a look here. So here we see the malloc at the top. Makes the new stack, which is called new, a bit confusingly because that's a reserved word in Java. It asserts it's not null, it checks that it worked. Well, in C, if it doesn't work, we'll raise an exception and we'll see what happens with that. So C will deal with it, Java will deal with that in a slightly different way. It assigns item count to 0. Well, that's what we did. We said this dot item count is 0. And here it said new dot item count. New arrow item count is 0. So notice the difference between the C and the Java. In the C, you're living outside the data. So if the data is called new, which is confusing, I'm sorry, and you want to set its field to be 0, you say new dot or new arrow, depending whether it's a pointer or not, new dot count equals 0. But in Java, the functions are living inside the object with the data. So they don't call it new. They say set my. Every function belongs to, every piece of data has its own functions attached to it. So set my data to 0. Set my item count to 0 is what's happening in Java. This dot item count. All right, here's what the pop looks like in C. Refresh your mind and then look at the pop in Java. We've got the same assert. We decrease the item count in the same way, except we don't say stack.itemCount minus minus. We say this.itemCount because it's when you're calling the function pop on some data, the this refers to the data that you're talking about. The data that the object that is the stack that you're popping off. And we return this.item, this.itemCount. So it looks exactly like the C. Does that make sense? It's just a different point of view. And one, you're standing outside the data describing it, and the other one, you're in there with the data. It's your friend, and you're calling it this dot that, this dot. Data and functions as belonging to objects. And you might think, that's a bit of extra work. Why would I want to do that? And we'll see next week that it's very convenient because when we've got an object and I give you an object, you now have everything you need to know to deal with that object and use that object. And that's very convenient because I can have 2 or 3 very similar objects and you can not care which one I pass you. Okay. All right. Ask me questions if you want to informally at the end now about task 2, task 1. Otherwise, I'll see you next week. So you can all go now, but make sure you go slowly. Everyone go down slowly. Hello. Meh.